Our problem here is to find the singular value decomposition of the matrix A, which is equal to 0, 0, 0, negative 4. The first thing we want to do is we want to find A transpose times A. So it turns out that A transpose is the same thing as A. So A transpose times A is going to be 0, 0, 0 in the first three slots. And then our last one is going to be negative 4 times negative 4, which is going to give us a positive 16. So here is the matrix that we're going to work with. This is the symmetric matrix that we're going to work with, where we need to find the eigenvalues and eigenvectors. So to find the eigenvalues, we're going to say that matrix minus lambda times I. So it's going to be negative lambda in the first slot, 0 and 0. And then in the other diagonal is going to be lambda, or 16 minus lambda. And then our characteristic polynomial, since this is a diagonal matrix, would just be the product of the diagonals. So it's going to be minus lambda times 16 minus lambda. This is going to give us our solutions for lambda. Lambda is going to be equal to 16 and 0. And in general, what we want to do is we want to put the larger number first when we construct our sigma, our diagonal matrix with singular values. We need to find the eigenvectors for each of these, and so we're going to take our lambdas and put them back into our determinant equation and find the null space. And so when we put 16 back in here, we're going to get negative 16. And we have 16 minus 16, which is going to give us 0. And that's going to give us a free variable at x2, and then x1 is going to have to be equal to 0 to make that negative 16 disappear. So our first eigenvector is going to be 0, 1. That's the eigenvector for 16. Similarly, we're going to put 0 in for our determinant expression here. And we're going to get 0 for the first slot, 0, 0 in the wings, and then 16 minus 0 in the other diagonal. And here we're going to have x2 is going to be 0, and then x1 is a free variable. So our two eigenvectors are 0, 1 for 16 and 1, 0 for 0. So we're going to construct our singular value matrix in the diagonals. And so we take a look at 16. Our singular values are going to be the square root of these values. So the square root of 16 is 4, square root of 0 is 0. So our singular value matrix that we're going to deal with is 4 and 0 in the diagonals. Now we want to construct V. So we're going to construct V by taking our eigenvectors and then finding its magnitude and divide by its magnitude so they can be normalized. Fortunately, these things have a magnitude of 1, so our eigenvalues don't change, or our eigenvectors will not change, and they'll remain as our column vectors for V. And we have V1 is going to be 0, 1, and V2 is going to be 1, 0. And so those are going to be our columns for our V matrix. In the expression that we're going to eventually get, we want V transpose, but the transpose of this is exactly the same. So we have our VT matrix. Now to find our U matrix, we want to find A and then apply that to the vector V. So our vector V was, our first vector V was 0, 1. And when we do this matrix multiplication, we're going to get 0 in the first slot and negative 4 in the second slot. So if we normalize this, that's again going to be 0 and 1, actually negative 1, because we're just dividing out the 4. That's the length of that matrix, or that vector. Now our second V is 1, 0. And we see that when we do this matrix multiplication, we're going to get 0 in the first slot and 0 in the second slot again. So unfortunately, this is not the way to find u. We still need to find u. So we're going to find u by doing, well, one way you think about it is the Gram-Schmidt process, but the other way is just to simply find another vector that's perpendicular to this. So there's many vectors that are perpendicular to this. Anything that's 0 in the second slot and any number in the first slot would work. And so the best candidate for that would be 1. And then we find our u vector 0, -1 in the first column, and then we're going to get 1, 0 in the second column. So you can go ahead and check that. We have our u vector that we just found. We have our sigma vector that we got from the singular values, and we got our v vector we got from the eigenvectors, v transpose. And when you multiply all this out, you should get 0, 0, 0, and -4. Okay? So that's it.